morning, everyone. We're just gonna give people just a little bit longer to start joining, and we'll start in about a minute. All right, we'll go ahead and get started. Good morning, everyone, and welcome to today's webinar. I'm Autumn Phillips, an R&D chemist here at Inorganic Ventures, and I'll be moderating this session. Joining me today is Mike Booth, our technical director here at IV, as well as Thomas Kozakowski, our stock production manager. Mike will be giving the presentation today on 5 essentials for ion chromatography applications. Before we get started, I just wanted to go over a few housekeeping items. So at the bottom of your screen, you'll find a Q&A box as well as a chat feature. Please submit any questions through the Q&A box, and we'll go through and answer them at the end of the presentation. The presentation is being recorded, and it will be available after in the next few days on our website. And you'll also get a notification for anyone who's registered for the event through email. So we'll let you guys know when that's going to be available to go back through and watch if some people aren't able to join us live today. Also, if you or someone you know is interested in some more in-depth ICP training, we have a new on-demand learning platform called IV Ignite that you can check out through our website. Registration is also now open for our 2024 ICP conference, which we host on site every year at our lab here in Christiansburg, Virginia. This is going to be a 3-day hands-on training where we'll cover all things ICP analysis, from sample prep to instrument maintenance to interferences and troubleshooting, and all things in between. So spots are limited, so sign up now. So without further ado, I'll go ahead and introduce our speakers for today. So our presenter today is Mike Booth. He is a chemist with expertise in quality control and instrumentation. His experience covers areas including ICP OES, ICP mass spec, ion chromatography, and various titration techniques. Today, Mike is the technical director at Inorganic Ventures. He received a Bachelor of Science in Chemistry from West Virginia University Institute of Technology. Thomas Kozakowski, who will be joining Mike and answering the questions at the conclusion of today's session, is a chemist with expertise in the manufacturing, quality control, technical support, stability, and homogeneity of inorganic metal standards. His experience covers areas including reagent synthesis and purification, trace metals analysis using ICP techniques, ion chromatography, transpiration studies, and container cleanliness. Thomas has a Bachelor of Science in Chemistry and a Bachelor of Science in Forensic Science from Virginia Commonwealth University. So both Mike and Thomas have a wealth of knowledge and experience in ion chromatography techniques, so we're definitely in good hands. And we'll be having some polling questions throughout the presentation, so just as a heads up, and we'd love to get your feedback on those. So with that, I'll go ahead and turn it over to Mike.
Awesome. Well, thank you, Autumn, for the introduction, and thank you all for joining us this morning. Ion chromatography is not a subject that we talk about a lot at Inorganic Ventures, but we have been running IC instrumentation and methods for a long time. So I'm excited to sort of start speaking about that more often. So as Autumn mentioned, those polling questions, if you get a chance to take the poll, that'll help us determine what more educational resources to send your way in the future. So let's go ahead and kick things off. And we're just going to give a quick rundown about what ion chromatography is. For those of you who entered questions and just sort of gave feedback on what you would like to see today, I want to extend a special thanks because I also noticed that a lot of folks are brand new to ion chromatography and may not have a good idea of what IC is or where it's used. So ion chromatography is a chromatography technique that is used in the environmental, pharmaceutical, food and beverage, and other industries. It's a very reliable instrumentation. It can give you extremely precise measurements, but the major downside that a lot of IC users face is sample throughput. It can take anywhere from 10 to 20 minutes and sometimes much longer than that to run a single sample. So sample throughput is always an issue with ion chromatography. The way these instruments work, there are, lots of instrument manufacturers. They all do a great job, and I'm going to sing their praises more a little bit later in this presentation. They all basically work the same. Your sample is injected onto an analytical column. Your column then is your sample is going to be pushed through with the mobile phase. And ion chromatography, that's called the eluent. We're going to talk more about eluent as well this morning. It gets pushed through the column. The column separates analytes based on ionic affinity. So think charge as opposed to something like HPLC that may do like size chromatography. The interesting part about ion chromatography is a lot of the instrumentation, not all, but most of it, the detector is a conductivity detector. So that's what the instrument is measuring. So after your analytes, in their mobile phase exit the analytical column, they're going to go through some sort of suppression. It could be an electrolytic suppression, or it could be a chemical suppression. And that helps reduce the background conductivity from your mobile phase. So that is a critical component to ion chromatography. And then finally, as I mentioned, the conductivity detector is going to read conductivity, and you'll start to see peaks appearing at different retention times. So how long they held on to the column will determine their retention time, and you'll see that through a conductivity measurement. Now, not all IC instruments rely on just a conductivity detector, though. So there are different detectors that you can get, and some applications rely on a different detector. So speaking of the different applications, here are some of the more common methods. So a lot of EPA and ASTM methods are available for just measuring anions or cations. One that I wanted to point out that is relatively new, especially in the world of environmental, is the PFAS method that the EPA is coming out with, EPA 1621. So that is a PFAS method by combustion ion chromatography, which essentially takes your sample, converts all the PFAS to just fluoride, and then you measure fluoride by ion chromatography. So interesting new technique there as well. We actually run more ion chromatography instruments at IV than we do our like ICP OESs, which is mainly what we talk about. But just, an idea, we do have IC standards available on the website. You can see that sort of screenshot on this slide. So if there's anything you are looking for, check out our website there. So let's start digging into the main topics. The first one is going to be your background signal. Your background signal is going to be dependent on your eluent. So if you have a clean eluent, your chances are you're going to have a lower background signal, which will improve detection limits. It'll just help things out in general overall. So having a good eluent and it being clean is critical. The eluent also impacts your analyte retention time. So as we sort of gave that a couple slides ago, we gave that rundown of how the IC system works, how the flow works through the system. The eluent is going to play a major role in your retention times. So since as your methods are validated, you want to make sure that everything is consistent. So how you prep your eluent is a big factor. And we actually have a resource on the Inorganic Ventures website under the technical videos. There's a short webinar, like a 5-minute webinar about making clean eluents. But the main gist of that is essentially if you're making your own eluents, you want to make sure you're starting with very clean eluent concentrates and very clean water. Even if your IC system is equipped with like an eluent generator, you still need to supply water to the system, and that needs to be very clean. So as clean as you can get things at the beginning, it's just going to help you throughout your analysis and get those background conductivities a little bit lower. We would recommend, if you are prepping your own eluent, to try to separate and designate lab equipment that's only used for IC, especially if your lab is also working with like nitric acid or hydrochloric acid. You can see those come up often in cross-contamination. So it's always good to designate IC equipment for IC use only. In our lab, for instance, we have graduated cylinders, pipettes, water bottles, and even a 20-liter container that's filled with DI water that we only use for ion chromatography applications. So it's always good to sort of separate that out and try to limit cross-contamination as much as possible. Lastly, I would just always mention, we mentioned this when talking about any instrumentation, keep a detailed maintenance log, and note the background conductivity, and note also when you prepare new eluent, if you are preparing new eluent. If you see a correlation in a new preparation of eluent and also, your background conductivity starts to rise, that might be a good indication that something was wrong with that eluent prep. Next up, we're going to talk about constructing calibration standards. So this is one, as we talk to a lot of IC users, this is what makes IC users, I think, stand out a little bit more from ICP OES or ICP mass spec users. A lot of folks that run ion chromatography will construct their calibration standards from stock single standards, as opposed to using like a blended standard. That's a perfectly good way to do it. If you do that, you're probably used to some sort of Excel sheet like we have on this slide here, where you have to keep track of all of your lot numbers, calculate up how much your aliquot should be, make sure you're recording that information, and then finally do a calculation on what your working standard concentrations are. So if you are prepping those up, we always recommend preparing standards by weight instead of volume, because you can get a more accurate measurement when you're measuring weight as opposed to volume. So we would always recommend that. And then this resource that we have here is one that's available from Ivy Ignite, our virtual training academy, which I'll mention at the end of the presentation. But I'm sure if you're prepping these up by hand, you have something very similar to this. A lot of the reasons that folks will prep up IC standards from stock single concentrates is stability can be an issue with IC standards, particularly anion standards. One way that you can get around this, however, is to modify the matrix a little bit. So this is an example of anion standards in particular have an issue with nitrite. Nitrite can convert over to nitrate pretty easily. However, you can correct for that by adjusting the pH to 10 or higher. So if you adjust that pH to 10 or higher, you can get around that conversion and you can stabilize nitrite. Phosphate will also tend to disappear over time. This is mainly due to biological growth, or what we call bug growth. So we get around that as well by adding a biocide component to our standards. Any of the standards that can be affected by bug growth that are mainly within a pH range where bug growth can happen. So adding a biocide can fix this phosphate stability issue. And this chromatogram on screen here is just an example. This is one of our stock blends that's available in our catalog. It's demonstrated stability for up to 5 years, and it includes nitrite, nitrate, and phosphate, along with some of the others that we refer to as the big 7 anions that we see coming through. So how you prepare your matrix for your standards can play a big role in the stability of them. Cations, you don't really have to worry about stabilization a whole lot. A lot of the cations are not going to run away or convert, but we do recommend stabilizing them in just dilute acid. We usually do 0.1% volume to volume nitric acid. We do get questions on occasion about stabilizing cation standards in acid, mainly because folks, I think, are concerned about the issue that can happen with overloading your analytical column. So this is actually called out in one of the ASTM methods that I've referenced on this slide. But it does also state that your method should be robust enough to handle 50 millimolar acid, which, if you work that out, is about 0.3% nitric acid. And that's, again, in your stock standard. So if you dilute that further in water, you're lowering that acid concentration. It's just a good idea to stabilize some of the cations in dilute acid, but again, you don't want to add too much. So that is something to be concerned about a little bit. All right, let's talk about combating interferences. So when you talk about interferences on ion chromatography, you're really talking about coelution. So this is a perfect example of a sample that was done on our main workhorse IC instrument. So this is the instrument that we have a method validated and set for. We don't really change it very often because it's used to test all of our custom products after they're manufactured and before they're shipped out. So we like to have that good to go and ready to run anything that may come up and not change it very often. So this sample had a mixture of fluoride, acetate, and formate. And as you see, when we put that through this system, you can definitely see two peaks. And if you're used to looking at ion chromatography, you can see the third peak in there in the middle, but they are not separated and it is just a mess, basically. So what we've done is we said, okay, this column is not really suitable for this. Let's switch out to another column. So we ran it on a different column that was more suited for low molecular weight organics. And when we ran it through at our normal operating parameters, we definitely see the three peaks now. They're not fully separated, but a lot better performance than the other column. And again, this is sort of a balancing trick that you have to do on IC is just getting the right column. And you also have to worry about, is your separation good enough, and compare that to your sample throughput rate. So in this case, they are looking good with this column, but we could probably do a little bit better job of the separation by changing the eluent concentration. So we went ahead and changed the eluent concentration from 15 millimolar carb to 2 millimolar carb. And you see this example now, we have really good separation, but we did have to pay that price in terms of analysis time. So in the previous example at 15 millimolar carb, our analysis time was about 9 minutes. For this run, where everything is nice and fully separated, we're looking at about 16 minutes. So that 7-minute difference that you're seeing there may not sound like a lot if you're measuring one sample, but if you got dozens of samples, that's where really the throughput can start to hurt. So always keep that in mind. The other thing you have to keep in mind that I mentioned kind of earlier, the IC will measure conductivity and it'll measure time. It does not tell you what those peaks are. You have to tell the IC software what the peaks are. So in this example, how do you know which is fluoride, acetate, or formate? The way that you can tell for sure is to validate retention times by running single standards. It's another reason why people that do IC will keep stock singles on hand. When they're tweaking their method or maybe validating a new method, you need to have those stock singles on hand to make sure that you know what the retention times are in your mixed standards or mixed samples. So doing this is a good way. It's not 100% guarantee because, again, there could be, especially in some of the organics, if there's something that you don't have a standard of, it comes out at a similar retention time. It's going to get you really close, but it's, again, not 100% guarantee for everything. For most things, you're going to get right where you need it to be. But again, just remember the IC only looks at conductivity versus time. I would also recommend when you're running these single stock checks, not to run them at too high of a concentration. Try to find out where the concentration range of your samples are, or like the midpoint range of your calibration curve. Because if you run them at too high of a concentration, the peaks are going to be a little bit too broad. You might not be able to narrow down the right retention time. So just keep that in mind as well. Other interferences that you have to worry about, the main one that other than just coelution, is going to be bleed over effects. So that's what we call a large disparity in concentration between peaks that elute closely together. So a classic example of this is sodium and ammonium. High concentrations of sodium, and when you're trying to measure low concentrations of ammonium, you'll see like an example in this chromatogram here. The sodium peak is just really broad and it's bleeding over onto the ammonium peak. This is a pretty common issue. And the way the industry, the IC instrument manufacturers have found to get around this is they have specialty columns if you need to measure low ammonium in the presence of high sodium. So that is one of those things where, as we talk method development, figuring out the right column for your need can be critical in helping you solve an issue pretty quickly. Other interferences to worry about is just the load on the column itself. So I mentioned before that sample is injected onto the column. If you inject too much sample onto the column, you may see your peaks start to front. which means that the peak will start to form, but it'll take a little while before the peak actually hits the apex and then drops back down. So you want to make sure you have good peak shapes. That's another important point for a good ion chromatography method. If you overload the column too much, you might actually see peak splitting, where the peak looks more like a doublet. So that is something to be concerned about. You can always reduce the load on the column by dilution or by switching out to a smaller sample loop. When you're measuring anions, you're going to have a water dip that'll be present. Sometimes that can cause an interference with your sample, especially we see it a lot when we measure fluoride. So if you want to get around that, what you can do is consider prepping your sample in your eluent to eliminate that water dip. That will eliminate it, but it just adds more to your sample prep. So again, it's a balancing act. And lastly, you may see carbonate peaks in your hydroxide eluents. This is something you can correct for by plumbing in a trap column into your IC, or something that we did in the past was keep the hydroxide eluent under nitrogen to prevent that carbonate from forming. That works as well. So let's talk a little bit about method development. When we talk method development, the first thing you want to keep in mind is, are you going to attempt to develop an isocratic or a gradient method? So the difference between those two is what happens to the eluent in your run. An isocratic method is going to keep the eluent at the same concentration throughout the entire run. So your eluent concentration is not going to change. And the main benefit to that is simplicity. I prefer those methods because you don't have to have as complicated hardware. And if you're troubleshooting, the simpler your IC system is, the faster you can troubleshoot and figure out what's going on. But sometimes isocratic methods are just not going to be suitable for your application. And this slide has a good example of a really tough application. Thomas, I believe, actually developed this method to separate out a lot of our cation inorganics and our organics together. So this is a huge list of analytes that we don't see very often, but we do see on occasion. And is there a good way to separate all of them on IC so that we can get good measurements for all these organics that are mixed in with some of these metals? So to do that, he had to set up a gradient method. And the gradient method is going to change the eluent concentration throughout your analysis time. So you can see the baseline in this one ramps up over time. That's because the eluent is increasing in concentration over time. In this example, it started off at 0.4 millimolar, and there's actually like 2 or 3 ramps throughout this run, and where it peaks off at about 120 minutes, that concentration of eluent is 8 millimolar. So we had to be really low concentration in order to separate some of the organics, and then drive it up to a higher concentration to get some of those metals off the column and through the system so we can actually read them. One thing to keep in mind when you're developing a gradient method that you may forget once, and then you'll probably never forget it again, is make sure that you change the eluent concentration at the end of your run to match the concentration at the beginning of your run, and give it enough time to sort of drop off or increase and equilibrate. So that's why you see it about that 120-minute mark on this one. The eluent, the background dives off and then starts to level out. That's where we changed it back to 0.4 millimolar and held it there for about 15 minutes. So that's critical to do. That is something that you'll, like I said, you may forget it once, but you won't forget it after that. And this particular run, again, we paid a pretty big price in terms of time for this. So this is a 140-minute run time. It does what we need it to do, and thankfully we don't have to do this method very often. So when you're starting method development, the best way to start that I've found is to pull resources from the instrument manufacturers. And I said I would sing their praises again in this presentation, and I just want to, again, say that now. They do a great job of putting resources out in the form of column manuals, white papers, and application notes. I would recommend, if you don't have your column manual for the column you're using, go ahead and download it. Download the column manual for every column you have, and download the column manual for every column you don't have. If you can get PDFs of them, they're very easy to search. So as you're trying to create a new method, you can open them up, search for the analytes that you're wanting to measure, and it'll point you in the right direction of where to go. They're really great about including sample chromatograms and all of those resources that give you the exact parameters, the column, the flow rates, the eluent concentrations. They may also recommend to use something like methanol or acetonitrile added to your eluent to help improve performance. That's something that is definitely pretty common in the ion chromatography space. But I would start with these resources, and then you can tweak them based off of your sample types. Other important settings to consider for method development is going to be like the injection loop size. I mentioned column overloading before. If you feel like you're overloading the column, you can always switch that loop size, or if you feel like maybe you're not loading it enough, if your samples are really dilute or really low concentration, maybe you can switch out to a bigger loop size. You can also change the column temperature if your instrument has the ability to do so. That can help improve performance quite a bit, actually. So that is something to look into. You can also change the flow rate, but again, IC is a world of balance. So as you change your flow rate, you may have to worry about pressure issues. Things I didn't put on this slide that you may want to consider: if you find the right column, but maybe you're just trying to improve throughput, you could look at, do you need a shorter or longer column? And does the column need to be a different size? So essentially the thickness of the column, you can go for a 2 millimeter column, or maybe you need a 4 millimeter column, or you switch the other way. Those can all be things that you can change during method development to improve your method. The last bit on method development, like I mentioned before, the instrument is going to essentially track conductivity over time, and it's really up to you to tell the instrument what the peaks are. You'll do this by, once you've ran your calibration curve, you'll go into the software and set this up. And this is really important to take a lot of care while you're doing this. A lot of the softwares are good about having, a program in that will automatically set your stop and start markers for your peaks. You can rely on that for sure. They do a good job. You can also tweak it manually. I would just make sure you're looking at those start and stop markers, especially ones if interferences are going to be present. If you're worried about bleed over between analytes, if you're worried about an interference because of the water dip on fluoride, for instance, make sure you're paying attention to those start and stop markers. The calibration model that it's using, you want to pay attention to that as well. Is it linear? Is it point to point? We've actually found that point to point it's better fit for purpose at lower detection limits. I don't really like point to point, but it does a good job sometimes at lower detection limits operating at low concentrations on IC. Setting the retention time windows is critical. Again, the software is going to call whatever peak that shows up there, what you tell it to call it. So if you say bromide comes out at 5 minutes and you give it a window of maybe 30 seconds on each side, if something comes out within that window, it's going to call it bromide. So make sure that you have those windows set correctly, that they're not too narrow or too wide. And lastly, because throughput is such an issue on ion chromatography, consider when you need to recalibrate. I mentioned earlier we have a workhorse method that we test all of our custom products on. We don't recalibrate that method daily. We actually recalibrate it every few weeks or so, and we test it each day by running a calibration verification check. Again, we don't want to spend the time to run the full calibration curve and then go through the software to fully recalibrate it. We don't do that every day. ICs are actually really stable if you keep them running consistently, and they'll maintain a good calibration curve for a long time, depending on your sample types and what you're putting through it. So that's just something to consider as well. Next up, we're going to get into troubleshooting. Troubleshooting, first off, is just I would say, worry about your baseline. If you have a good stable baseline, you're at least in a good spot to start. And if you don't have a good stable baseline, then it's not really any point in running anything. So the example on this slide shows some baseline measurements. They're all overlaid. This is all total conductivity, not corrected for anything. And you can see we've got some weird baselines going on here. So this was a key to us to say, okay, we have to stop. We can't run anything until we figure out why the baselines are changing so much. To troubleshoot this, I would start off with checking the eluent concentration. Check the pumps and the check valves. The check valves are near the pump heads, and that they're mainly there to prevent backflush or backflow of eluent, that it shouldn't go backwards through the system. So you can check those. Check valves need to be changed out occasionally. If you're really seeing issues with baseline and you can't quite figure it out, I would try injecting water. We've had good luck with that in the past. We have baseline issues. We run maybe like 3, 4 vials of water, just real quick run times, like maybe 5-minute run times for each. And then we get a stable baseline. So you can try that as well. Not quite sure why that works sometimes, but it does work. If you see peak tailing, that just being, your peak comes out, it looks fine, but it just has this big long tail. That's usually an indicator of some sort of dead volume in your plumbing on your system. So just go through, check your connections. You might need to trim some of the tubing, make sure everything's seated correctly. You can trim just the ends off of it, reseat it, make sure everything's at the right tightness. And that should fix peak tailing for you. Peak walking, that just sort of refers to a change in retention time over time. So maybe chloride came out when you did a fresh calibration, chloride came out at 4.5 minutes, and now it's coming out at like 4.75 minutes. A few months later, that is relatively normal over time. The column is going to change over its lifetime. That's why you want to be really sure that you've got your retention time windows set correctly. And that's a good indication of when things are falling outside of those retention time windows, you might want to recalibrate. So it is common over time. When it's not common is when it changes a lot from injection to injection. So if you're, one injection, your retention time changes by a great deal to the next injection, that might be something indicating you have an issue with your flow rate, or maybe there's some sort of issue with how the sample is getting injected onto the column. Is something getting stuck or hung up? It's not injecting at the right time that the instrument thinks it is. I would, if you see that, I would focus mainly on injection valve and before the injection valve and the pumps to try to fix that issue. Broad peaks are pretty easy to fix most of the time. Usually indicates that just the sample's too concentrated. If it's your sample itself, you can try to dilute the sample. If it's the column that's overloaded, you can try a smaller injection loop. That should work for broad peaks. Poor resolution, like in the example that we have on this slide, this is our big 7 anions before. And that chromatograph that we saw for that product that had 5 years of stability, they had great separation. This one, not so much. So in that case, it could be the sample that's causing that. So you can always run a control sample to check just to make sure that your control sample has good separation. If your control sample is also looking really poor, double check your eluent first and then start going through the system. Is there some sort of tubing that needs to be replaced that might be dirty? Just do a good clear of the whole system. And then if you can't find anything, you may want to check just the column age. Columns usually don't go bad overnight unless they have something injected onto them that's really bad for them. But columns are consumable. They're an expensive consumable, but they do go bad over time. So if you see performance dip in terms of separation, in terms of detection limits, you may have to replace your column to correct for that. And lastly, on troubleshooting, we're going to talk about pressure issues. Mainly when things go over pressure, that's when you have to really worry, because you're probably going to blow a connection tubing or a tubing connection. Something will just pop off. So if you're running into high pressures, you can clean your check valves. You can replace your check valves. Again, those are near the pump heads. You can clean the injection valve or rebuild it. This is something that we've done on our instruments quite a bit. That injection valve does physically move, so it can experience wear and tear. It can get dirty. Trim or replace tubing. You shouldn't have extremely dirty tubing after your analytical column. So if you're worried about dirty tubing, I would say anywhere before the analytical column is what you may want to replace. Anything else you may want to trim up just to make sure that the connections are still good, that the piece of tubing hasn't been like crimped off. That can cause high pressure issues, especially if you over tighten something. You can see high pressure issues. If you have experiencing low pressure issues, usually a good indicator of a leak. So those are usually easy to spot if your flow rate is relatively high. If you're running a low flow rate, it may be hard to see it. So what you can look for is look for dried eluent. So the flow rate is just so small, you don't see droplets forming anywhere in the system. Look for the presence of like dried salts, crystals, anywhere near connection points. or anywhere near the bottom of the instrument itself. If you can see, where it's dropped off of something and just dried up on the bench or dried up inside the instrument near the bottom, that's a good indication that you have some sort of leak. That you just need to go through, again, check your connections, check their tightness, trim off the ends and of the tubing and reseat them. And then lastly, for pressure issues, listen to your pump motor. A lot of times on IC, you're going to be working at the instrument quite a bit, loading it up, um, setting the software for your calibration curve. You'll get a good feel for what the instrument sounds like. If it starts to sound different, that's a good indication that maybe something is wrong with the pump. And that's a good time to call your instrument manufacturer and just see if everything is looking normal, if they have some sort of troubleshooting you can do for the pump itself. So as I mentioned, we here at Inorganic Ventures are here to help. Like I said, we don't talk about IC a lot. I really appreciate the feedback you have been giving us in terms of the polls. That's going to help us determine what resources we can focus on and make available to you guys next. But if you are looking for anything, check us out. We do have stock singles and blended standards available, including some of the organics, which a lot of people don't know that we do. We do organics for ion chromatography users. So we have a library of those available if you need them. We also have the IC standard product line, comes with chromatograms and the C of A, and they're also really good for colorimetric testing techniques. So if you're running like a discrete analyzer or a benchtop UV vis and you need like a chloride or a phosphate or a sulfate standard, we would recommend our IC products. They're extremely suitable for those techniques. And lastly, I mentioned, before, a lot of IC users prep their own working calibration standards or their main stocks, their main blended stock standards that they dilute down from. If you're looking to save some time, reach out to us. Our custom product development team is here to help. They can save you sample prep time. They'll work with you to see what your needs are. They can provide you a free quote with guaranteed stability on the product. So if you're looking for that, it's a good place to start. And lastly, how we end almost every Inorganic Ventures presentation. If you have any questions about if you need resources, check out the website. There's a great resources there. We have a podcast that comes out every Tuesday. And as I mentioned, we have Ivy Ignite, which is our virtual online trading academy. So all these slides have QR codes that'll take you there. And then very last, as Autumn mentioned at the beginning, spots are filling up for the 2024 ICP conference. So if you are interested in that, reach out to us and we can get you signed up for that. But there is a lot of hands-on lab time at that conference, which really sets it apart from most others. And with that, we'll go ahead and change over, and Thomas will join us for questions. Thank you all.
Awesome. Thanks so much, Mike. That was a great presentation. So if you haven't submitted any questions already, we're going to go through now. Just submit your questions to the Q&A box, and we'll go through and answer those at this time. So it looks like we have a few here already. The first question is, in what way do methanol or acetonitrile improve performance? So I think those are more often used for HPLC methods or LC methods, but it really depends on what components you have in your sample that you're trying to resolve. But that's going to affect anything from your peak separation. The concentrations are and the gradient is going to affect how well you're able to resolve those peaks. It's also going to affect your background, the pressure of the instrument. So it really depends on what you're trying to detect. But do you all have anything
Yeah,
else?
I was reading the manual for our CS18, so we use that one for the method that Mike showed with the big gradient for 2 hours. Acetonitrile can be used on that column to help clean it up. So some of those organics might get stuck over time to the column, and that's a great way to rinse it out. So if you include that in part of your method, you'll have less buildup over time and should improve your column performance.
Yeah, I think mainly it's used a lot for some of the organics, and it changes kind of like the polarity of the eluent a little bit. From what I've read, it sort of helps those come off the columns. If you're seeing like some differences, things are sticking to the column and it's an issue of polarity, adding those can really help. But I would suggest, I wouldn't add that to your eluent if you're looking at just inorganics. Nothing that I've found really seems to add those. That I really worry about it if you're looking at organics.
Awesome. So the next question is, we observe a chloride interference for nitrite test. Our FP solution contains 0.9% sodium chloride. Do you have any suggestions for how to correct for that interference or remove that?
Yes. So there are different things that you can get to treat your sample before you, it's sort of like a filter. So I know, Thomas, I think you've messed around with some of these for the cation systems, but I believe there is a filter that can help strip chloride out of your sample. And you can either put that in line, or I believe that Thermo has it where it's the filter cap on the actual vial itself. So as the auto sampler injects the sample, it pushes it through that filter cap. I believe there's one that can strip out chloride. So I would suggest looking into different filters that you can either put in line or sample caps. The sample caps are definitely more pricey from what I remember, but there are some options that can help with that.
Awesome. So the next question deals with the nitrite-nitrate stability in solution. So if you have samples with nitrite and nitrate and wanted to increase pH to stabilize the nitrite, what would you recommend adding to preserve those samples?
Yeah, Autumn and I can definitely answer this one. We've manufactured standards when we first started here. So whenever we make these anion standards, we typically pH adjust with sodium hydroxide. So honestly, a pH strip is good enough. We check that it's a greater than 8. And like Mike said, when nitrates or nitrites involved, we try to go a little bit higher. We do that for oxalate as well. So if you keep that above 10, it usually keeps everything happy. But if for some reason you don't want sodium, because maybe you're doing both types, potassium hydroxide is perfectly fine. I would say ammonia is probably not as good because over time the stability of that could change.
Yeah, thanks, Thomas. So the next question, if you could suggest a method for separating organic acids, acetic, formic, butyric, and propionic, that would be great, including column eluent flow, etc.
Yeah, that's a good question. So for those, we actually work with those in their base form. So the example that I provided earlier was acetate, formate, and fluoride. If you want to separate them as the acids themselves, I would say, well, I can look into that and send you an example. It'll probably come out with the, usually after webinars, if we run over time and can't answer all the questions, we'll give out a list of all of the questions we didn't get to. So I'll make sure this one's included in that list, and I should be able to find something that would be able to, that I would recommend for these if you want to measure them as the acid forms.
I do know there's when we look at these acids, we generally do these on our Metrum instrument. So I think Metrum has a really good column for this. But unfortunately, I don't have the specific settings on me. But Jody would be the best person to answer that.
Yeah.
Awesome. So the next question is also something that we don't have instrument capabilities here of doing. So we may have to also answer this one afterwards. But the question is, if IC is coupled with ICP mass spec, what sample flow can ICP mass spec tolerate, and what nebulizer should you use?
I
Yeah,
mean, I
that's
can speak a little bit to this too. I mean, if you're doing mass spec, or ICP mass spec, you're looking at inorganics, so you're probably looking at a cation system. So things like calcium, potassium, sodium, etc.
Mm-hmm.
Mass spec, the flow rate is dependent on the nebulizer. So you would want to choose a nebulizer with the right flow rate. I mean, you go to the ICP nebulizer manufacturers, they've got ones that can do really low flow. You can do ones that are really high flow. So you might want to just match that with what your IC wants to do for your column, and go from there. But I don't see why you would have an issue with an inert like PFA nebulizer or even Boro glass. I don't. I think either should be suitable.
Yeah, this is something we can definitely look into more, but I would just, my thought is, since we don't have one of these in our lab where it's tied into an ICP mass spec. I would worry about the flow rate for your IC first. Make sure you're getting good separation, because that's really the whole point, is making sure that you're introducing those one at a time into your mass spec. So whatever the flow rate is of your IC, I'm pretty sure you'll be able to find a nebulizer that can handle that flow rate. It's just, again, I would base the nebulizer choice, like Thomas said, off of your flow rate from your IC.
Right. Yeah. And if you have a concentric nebulizer, which is what, is kind of a standard in most labs now, those have pretty low sample flow rates anyway. So I feel like it would probably work, but like Thomas and Mike said, we can look into that a little bit more and provide more feedback if you need. So the next question, I always work with Dionix instruments. Now I've been introduced to Metronome instruments. I have had issues with baseline and peak separation. Every time I run a sample, I have to adjust retention time. How can I fix this?
Yeah, that's a good question. And I know one of the other questions was, which IC vendor do we currently use? We currently have instruments from Thermodynamics and Metronome. So we have experience with both. With this, it sounds like it might be an issue. Metronome uses a chemical suppression system. I would focus attention on that first. But I would also reach out to Metronome and just send them your chromatograms. I think they have a certain file type that you can send their tech support team that gives them they're able to see all the instrument settings that you're using. We've reached out to both vendors before and gotten really good technical support. But I would just focus more on their suppression system, because it is very different from the Dionix suppression system with the electrolytic suppression add-ons that they have.
Yeah, the only thing I'll add to that, I mean, Jody, she's not with us with answering questions today, but she's our resident expert. The most common troubleshooting I hear about for our Metronome instrument, though, is some of those filters and the check valves. So, like Mike said, focus on the suppression system, but you might want to check those filters too, because every once in a while we run all of our organics on it, and sometimes they go fast, much faster than you'd expect. So I'd focus there as well.
Yeah, and just also make sure that you're allowing the instrument enough time to equilibrate at the beginning. So with our Metronome, I don't know if it's the same as the one that you all have, but we make sure that there's a little dip when it switches to the different valve position that Thomas was talking about. So we make sure that it has time to go through each of those switching positions, which you can see by a little dip in the baseline. So just make sure that you're giving it a good amount of time to equilibrate too.
Yeah, I think Metronome calls that like the step time. When it's just equilibrating or running idle, you can set a different step time to let those suppression chambers cycle.
Yeah. All right, awesome. So the next question, if you want to preserve a sample for phosphate, what biocide do you recommend and at what concentration? How can you be sure the biocide will not damage the IC instrument and column?
This is a good question. So our biocide is something that we kind of keep as a house secret almost. I'll look into what information we can provide about the biocide when we send out the rest of the emails. But that is a very good question about what concentration and how can we make sure it doesn't damage the IC instrumentation. The concentration is about 0.1% that we add into it. And the only thing that we've seen is if you run higher concentrations of it, it does appear to be something that comes out about the same time as nitrate, at least on our main workhorse method. If you run that biocide by itself just in water at a higher concentration, you can see something that would appear to come out at the same retention time as nitrate. Whether it's nitrate or not, I don't know. It could just be sharing the similar retention time. But I'll try to see what we can't find to supply in terms of what we would recommend for a biocide. But there are many out there. You can always just I don't think that they're too costly. You can always experiment with some. I'll sort of leave it over to Thomas for what he thinks of selecting a biocide.
They might be hard to get because those are much more regulated. Because I mean, if you have accidental release, it's obviously an environmental concern. Um, Mike said it was 0.1%, but really it's 0.1% of like a 10%
Yeah.
solution. So the concentration is very low. By the time you do dilutions for working standards, it's even lower. If you end up having problems with your column, again, one of those column rinse procedures would take care of it. It's really just an organic that isn't polar, so it'll wash right through most of these mobile phases or your columns.
And something I'll add to that is I know this is something that one of the questions that came in beforehand was talking about how to extend like the lifespan of the column and the instrument, some of the consumables that are very costly. Filters are your friend. And also if you can get a guard column, which is essentially the same column size, it's just a shorter version. So like I think they're usually about 50 millimeter in length for thermo, and then it's just a little add-on for the Metrum ones. They just they screw right into it for the Metrum ones. That can sort of help take the brunt of damage, so you don't have to replace your analytical column as often.
Okay, awesome. So the next question is, let's see. Someone asked which IC instruments does IV currently use?
Yep. So we do. We have some thermodionics and we have a Metrum. But I believe there are others out there as well, like Shimadzu and Waters, I believe, has IC systems. I've not really, like I said, I use resources from all of them. So all of them that I've spoken to have been really nice to work with. And you can get resources from all of them. You can also, you know, I don't think that they like this, but you can run each other's columns on different ICs. Like we ran thermo columns on our Metrum. We ran, I think, Metrum columns on our thermos. It's all what's the best column for the application that you're going for.
Awesome. So the next question is, can you suggest any method for chromium speciation by ICP mass spec? And do you sell any chromium speciation standards other than Chrome 6 and Chrome 3?
Yes, so this was actually one of the questions that came in ahead of time that I was able to look into a little bit further. So there are different methods, and this is a great example of maybe using a different detector would be better for IC. So the example that I found, there was I believe it was a thermo method. We'll make sure to send this out with the questions that we didn't get a chance to answer. I believe there's a thermo method that used a UV vis detector for separating out Chrome 3 and Chrome 6. And I think it paired with might be an Agilent mass spec or something. Maybe it was a Metrum IC and an Agilent mass spec. But that is something where you can use a different type of detector and a different type of column. The eluents for that one was a little crazy as well, but they were able to get that separated and then do analysis by ICP mass spec, which is a very interesting application note. The way that we determine Chrome 3 and Chrome 6 in our lab is we do Chrome 6 as chromate and we run it as an anion. And then we do total chrome by ICP and we just subtract the Chrome 6 from the total chrome. So there are different ways that you can do that, but I will find that application note and make sure to link it in the responses we send out afterwards.
Alternatively, I mean, we're doing IC now, but we used to use UV vis for the Chrome 6. So it's got a specific wavelength that works really well. So I don't see any issue with trying to get Chrome 6 to work with a UV detector. I do know that Thermo has those. I'm sure the other instrument manufacturers do as well.
Yeah. And just to answer the other part, we only sell the Chrome 6 and the Chrome 3 speciation standards.
Awesome. The next question, is there a method developed for separating isomers of organic acids, like valeric and isovaleric acids?
I'm sure there are. We don't have experience with those specifically, but this is
Mhm.
where you want to go to the the column manuals and look at their example chromatograms. A very good resource if you don't have access to it, you might want to purchase it. Is Thermo's virtual column. They have a huge database where you select which ones you want to look at, and it will recommend the columns, eluents. Um, it's a great resource. I think last time I tried to get that quoted, it was like 600, but well worth when you're doing method development.
Yeah,
Yeah, I
that
would.
is super
Oh,
helpful. Sorry, Mike.
I was gonna say I'd definitely reach out to some of the column manufacturers for that, because that one may be more challenging for ion chromatography. Um, I would say also, we didn't touch on this in this presentation. And like I said, if you guys provide feedback that you're interested, there is also like ion exchange and ion exclusion chromatography that we didn't really touch on today at all. But those can play big impacts on what you can measure and how the methods can be validated and what's actually a better method for some analytes.
Yeah. All right. Looks like we have two more here, so we're going to try to answer that. I know we're running up on time, but we'll just try to answer these last two live. So the first one is, we're running LC coupled with ICP mass spec method for arsenic speciation and have started using 5% methanol in our mobile phase. Would you expect this addition to affect the plasma/detection?
Yeah, that's definitely one of the things that we recommend in our ICP conference. You can add methanol to get higher signal for arsenic, so that should give you better detection limits. Um, if you couple that with some of those specialty nebulizers and spray chambers meant for arsenic, you can probably go pretty low.
Yeah.
Yeah, yeah. So there is a pretty, or there are some pretty significant carbon interferences that we've observed, um, especially in the lower UV range, which is where your most sensitive arsenic wavelength is going to be. Oh wait, you said mass spec.
Yeah.
But yeah, carbon does cause interferences on mass spec as well. So yeah, I think also just ensuring that you're um, matrix matching appropriately for that methanol, so that you're able to account for any of the carbon interferences.
Yeah, I would say just matrix matching your standards to account for that should be good.
Mhm. Um, so the next one, can you please elaborate on sample prep and eluent to eliminate the water dip?
Yes, that is actually something that one of our customers helped us discover. And when you think about it, it makes a lot of sense. So as you inject your sample onto the column, you have to think that your sample is usually prepped in water. So that water is going to dilute out the eluent. You're going to see a change in conductivity as it flows through the sample or as it flows through the system. We actually had a customer request their matrix of their IC standard be prepped in, it's actually the same eluent that we use on our workhorse method. So it's a mixture of carb and bicarb. And we ran those samples. We noticed the water peak was reduced. The water dip didn't go down as far as it usually would. So he just was like, well, I wonder what happens if we just take some of our eluent and inject it in place of water. So we had some extra eluent prepared. We ran it and it stays flat. So we've made standards in this. So essentially, instead of prepping in water, if your eluent is 2 millimolar carbonate or 15 millimolar carbonate, you prepare in that 15 millimolar carbonate, and you'll see that water dip go away.
Yeah, and another thing to keep in mind when you do eluent preparations for your sample, you'll if you're using a second source, you'll be able to tell which source is dirtier for those components. You'll We were surprised when we made our own for the first time. We were actually seeing dips, which was telling us that what we were testing was actually a cleaner than what we were purchasing for our eluent, which was quite fascinating. But yeah, if you see dips where you should see peaks, and you're doing that kind of preparation, that'll help pinpoint some contamination you might have in your eluent source.
Yep.
Awesome. I know I said the last one was going to be the last question, but there is just one more I want to answer really quick. So this person said that they have samples with nitrite and nitrate. They do adjust to a pH 8. After measuring 2 samples, they have problems with the control standard, and recovery drops for 10 to 15%. And so they're outside of their control limits. One thing that I would recommend for that is just ensuring that you do pH adjust before adding the nitrite to make sure it's always in that basic media, because you could be losing it before the pH adjustment. So that's what we would do in our lab, is we would ensure we would do a pH check and make any adjustments before that nitrite is ever introduced. Do you guys have anything else?
Yeah, you're right. We forgot to mention that order of additions for that is critical. So we usually have a higher risk of pH issues when higher phosphates involved, because our source of phosphorus, or phosphate in this case, I believe is only monobasic and not dibasic or tribasic. So it'll bring the pH down to like 5. And that'll obviously wreak havoc on nitrite, oxalate, and a couple others. So high phosphate, be wary depending on your source of standard.
Yeah. All right. Well, I think we're about out of time for today's webinar. Thank you guys so much for joining us today. And again, the recording of today's presentation, along with the downloadable slides, will be available on our website in the next few days. So if you want to come back and reference it, or if there's anyone else you know who may benefit from the information presented today, please feel free to share that. And that will conclude today's webinar. We hope you guys have a great Thursday. See you at the next one.
Us.
Thanks.